All right, here are perfect problem 1 solutions for Math 211. What's going on here is I'm talking about, it's called graph theory, an important topic in math, one that I really like. And the idea is to kind of put down vertices. So here's one vertex, here's 2 vertices, here's 3 vertices, here's 4 vertices, 5 vertices, 6 vertices, and then try to connect the vertices with straight lines. And there's a little bit more to that. I mean, you have to put the vertices in the correct spot. You kind of can think about it as putting them on a circle or something and then connecting them all with straight lines. At any rate, the question is, how many lines would you need to connect all the vertices? So let's see, vertices, lines. If we have one vertex, we need 0 lines. That's this case right here. If we have 2 vertices, we need 1 line. If we have 3 vertices, we need 3 lines. If we have 4 vertices, we need 6 lines if you go through and count all these. If we have 5 vertices, go through and count, and I think you'll find you need 10 lines. 6 vertices, check out, keep going. 15 lines. And 1, 2, 3, 4, 5, 6. I guess that's all that's pictured. So then the question becomes, can you see a pattern going on here? And I think you can. What's going on is we change from this line to this line is we're adding 1. And from this line to this line we're adding 2. And here we're adding 3. And here we're adding 4. And here we're adding 5. So another way to describe this 15 is it's really just 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 plus 3 plus 4 plus 5 is 15. That's where this comes from. So if I want the complete graph on 6 vertices, I need 15 line segments. But that's not what it asked. The question asked me how many line segments would be necessary to create a complete graph on 100 vertices. So what if this kept going? All right, what if this went all the way down to 100? Well, maybe we can follow the pattern. Just like 15 was 1 plus 2 plus 3 plus 4 plus 5. To get up to 100, it would be 1 plus 2 plus 3 plus 4 all the way up to, well, let's see, this one stopped 1 short of the number of vertices we had. So if I wanted to stop 1 short of 100, I'd be stopping at 99. So this is my answer right here. I just got to figure out what is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, 11, up to 99. We learned in class you can use Gauss's method for this. So maybe I'll do this off to the side. Kind of short on room already. To sum 1 plus 2 plus all the way up to 99, we can use Gauss's method, where you rewrite the sum underneath it, except in decreasing order. And what you notice is that every single column sums to the same amount. In this case, every column sums to 100. So then the question becomes, how many columns do you have? Well, I have 99 columns. 99 times 100 is equal to 9900. But that's the sum here, right? This sum is equal to 9900. So the sum 1 plus 2 all the way up to 99 would be exactly half of this number. Well, half of this number is what, 4950, I believe? So that would end up being the answer to the question. 4950. It's the complete graph on 100 vertices. You'll need 4,950 lines. Okay, so for part B, the problem changes a little bit. You can only draw 10,000 line segments, and the question is asking what is the largest complete graph you can draw. So now we're kind of working backwards. Right? Instead of being told how many vertices we have and asked how many line segments it would take, we're told how many line segments and asked how many vertices it could take. For part B, I think guess and check will be really useful. So recall that when we had 100 vertices, what we did is we summed the numbers from 1 to 99. And to sum the numbers from 1 to 99, we took 99 and multiplied it by 100 and divided it by 2 to get 4,950. So we're going to need more than that. Right? We don't want 4,950, we want 10,000 line segments. So maybe we try 200. Well, let's see, following this pattern here, 100 was 99 times 100 divided by 2. 200 would be 199 times 200 divided by 2. And maybe plug that into a calculator or something, you'll figure out that's 19900. In other words, 19,900. Oh, that's too many. I only wanted 10,000. I better choose something less than this. How much less? I don't know, maybe 180. 180 would be 179 times 180 divided by 2. And for that, I'm going to have to pull out a calculator. Fortunately, I have one right here. 179 times 180 divided by 2 gives me 16,110 vertices. Still not quite there. All right, what about 160? 159 times 160, let's keep this in the same order, divided by 2, is getting closer, 12,720. So let's kind of continue this over here. I have vertices, lines. I want less than 160. I don't know, maybe 150. Well, for 150, I do 149 times 150 divided by 2. And I get 11,179. 11,175. I don't think that's what I said. So I'm getting closer, maybe 140. Well, 140 would be 139 times 140 divided by 2. If I do that calculation, oh, I'm too low. 9,730. Getting close, though. All right, I want to add a little bit more. I don't know, 144 would be 143 times 144 divided by 2. A little too high. 144 was 10,296. About 143. 143, to figure that out, I do 142 times 143 divided by 2. Getting close. 10,153. That's 143. Hopefully 142 will be the last one I have to do to figure out how many line segments it takes to draw the complete graph on 142 vertices. I'll do 141 times 142 divided by 2. And I get, oh, very close, 10,011. So my answer is going to be 141, because 141 is going to be less than 10,000. I guess I should prove that. 140 times 141 divided by 2, and I get 9,870. So I only have 10,000 lines. I can't draw 142. Could draw 144. This is the most vertices for 10,000 line segments. Whew, all right.